Okay, everyone. So I am back. This will be part 3 of the lecture for chapter 8. Remember, at the end of chapter 2, I had just gone through and talked about the 5-step model. So just as a quick recap, there are, like I said, 5 steps to the model. And what you see here on the screen, these are those 5 steps. The stuff that's highlighted, the Z critical, that is the Z-score that marks the beginnings of the critical region of the Z distribution. So that's typically like that's the Z that corresponds to your alpha level. I'll put it that way. So if I have an alpha of 0.05, then my Z critical, depending on the type of test I'm doing, will be it'll be Z equal to 1.96. And then of course the test statistic, that's the number that you get when you do step 4, which you will see in a moment. And it's essentially the Z obtained. The Z obtained, that's the statistic that's computed in step 4 of the 5-step model. I'm giving, even though those are essentially related to the same thing, I'm giving you the definition or the information for both of them because you'll hear those terms or you'll see those terms used throughout parts of the hypothesis test. So I just want to make sure you know and understand that. Okay, so let's go ahead and start going through these steps. All right, so here's our model, or here's our example. We're going back to the education example. So you remember in the education example, in the education example, we have the education majors. So remember, education majors have much higher GPAs, okay? They have much higher GPAs than students in general. So that's the thing that we're looking at. We know that the mean GPA for all students is 2.70. So that's our population GPA. The number, the random sample, the number is equal to 117. And the sample, because our sample, those are our education majors, that's the group that we are comparing to the overall population. They have a mean GPA of 3.0. Now, we don't have the population standard deviation. They didn't say that up here. Remember, when you're looking at problems and you're looking at these questions, look at what's in there very carefully. If they had said the mean GPA for all students is 2.70 with a standard deviation of ... If they had said that, then we know that's the population standard deviation, but that's not what this problem says. It's telling us we have a random sample of 117 education majors whose mean, with the mean GPA of 3.0, with a standard deviation of 0.70. This question is even giving you the clue. It's giving you the symbol for a sample standard deviation. And remember, it's important to look at all of this type of stuff because this is where those formulas start changing and you have to pay careful attention. You can't just use the same formula for everything. All right, so step 1. So that was just, that right there was just the information for the problem. But what we'll do is use that problem and that information to talk about things that you see here. So if you want, you can look at page 191 because 191 is where the different steps are listed out, but it's also where the book starts to give you a little bit more detail about what some of these different things are. So hopefully you remember the equal probability of selection method. This was covered in chapter 6, and it deals with the methods used to maximize the probability that the sample will be representative. Okay, so basically, when it says random sampling, that's what they're talking about here. They're talking about, okay, let me back up. Step 1, you have to make these assumptions, right? There's 3 assumptions that you actually have to make when it comes to a hypothesis test. You can't just go out there and say, oh yeah, I'm just gonna go do a hypothesis test, even though that's essentially what we're doing when we practice these problems. But in reality, when it comes to research, you can't just say, I'm just gonna go do this test. There are certain assumptions that have to be made. The first one is that random sampling has occurred, okay? That random sampling has taken place. You also have to look at the level of measurement and make sure that it's interval ratio. And you also make the assumption, or the assumption is that the sampling distribution is normal in shape. All right. And so this is what I was, so now I can back up and talk about the equal probability of selection method. So random sampling, again, this is what was covered in chapter 6, and it deals with those methods to make sure that you do in fact have a random sample. It's the methods that are used to maximize the probability that the sample will be representative, because hopefully you remember, but if you don't, just go back and refresh your memory, or I'll refresh your memory for you. In order for a sample to be representative, or to increase that probability that a sample will be representative, you do random sampling. And that's where, or you use some type of random sampling technique. Because remember, there were multiple random sample techniques, but you basically do that. So here, we know in the problem, we're told that the sample of 117 education majors was randomly selected, okay? But the next assumption for this type of testing, you assume, or you have to basically be able to say or show or demonstrate that you're using interval ratio data, or the information that's being examined is at the interval ratio level. Your variable is interval ratio. And this is one of those levels of measurement that was discussed in chapter 1, if I remember correctly. But this is where the scores of the variables are actual numbers that can be analyzed with all possible statistical techniques, okay? So this basically means that you can add, multiply, compute averages, get the square root. We can basically perform any mathematical operation with interval ratio variables. So if the numbers, or if what you're using is categorical, you would do something different. And that's something that I'll talk about at the very end. Now, sampling distribution. Did I? Yes, I did. Okay. Sampling distribution. This is basically chapter 6 again, that distribution of all possible sample means, is normal in shape. So this is what allows us to use this allows us to use the standardized normal distribution to find areas under the sampling information or sampling distribution. Now, the thing about it is the information that you'll see in these steps is typically written in abbreviated form, okay? But here I have all the information basically so that you can understand what's going on. It gives you an example, and it talks about these different things. So random sampling, the level of measurement, it's basically breaking that information down so that you can see how we're making these assumptions. Now the information, again, like I said, that's in this step is usually written in an abbreviated form. And an example of this appears on page 192 of the course textbook. And I'll show you this when I work through some of the examples. And when I demonstrate how to do this, I'll show you what it's supposed to look like. All right, so I'm not going to go through and rehash the information from the question. Hopefully you took that information down from the previous slide. All right, so again, that was step 1, but now we're on step 2. So step 2, this is where you state the null hypothesis. All right. You state the null hypothesis. So basically what's happening, or just to kind of give a little bit of an explanation, the null hypothesis, and as a recap, the null hypothesis states there's no difference between your two groups. So in this instance, it was the education majors. So the null hypothesis is basically saying there's no difference between the education majors and all other students. All right. But the research hypothesis also has to be, or is also going to be stated at this point. So your null hypothesis, that's the one at the top. So let me highlight that for you. Here's your null hypothesis. Okay. And just so you don't get them confused, I will change the color to blue. This is the alternative hypothesis or your research hypothesis, all right? So again, the null hypothesis, the one highlighted in yellow, that's basically saying that there's no difference between sociology majors, between education majors and all of the students. There's no real difference between the two. Whereas your research hypothesis is basically saying, yeah, there's going to be a difference. Doesn't say which direction that difference goes in, but there is a difference. Okay, so that's what's essentially happening right here, and that's what those two numbers state. And what I have highlighted in yellow and blue, that's what you would actually put in the problem or in your when you write all this out and you are when you're typing it up and you're putting all the information, when you are doing this for the assignment that's going to be coming up, that's what you would write. You don't need to write all of this other information. So give me just a second. So all of this information right here, all of that, and all of this information that's in between the red squiggly lines that I got going on, you don't write all of that, okay? This is what you write. This right here, you write that number or that mathematical equation, and you write that one, okay? It's a strange looking arrow, but you get the point. That's what you write when you are doing the hypothesis test or when you are writing everything out, okay? All right, so step 3. Step 3, this is basically, okay, let me highlight. Actually, no, this one I'm not gonna highlight and say what you do and don't write. I'll show you when it comes time for some of the examples. But for this one, this is basically where you're gonna end up using Appendix A for this, okay? This is where if you went back and you were gonna find the areas under the sampling distribution. So in this particular example, we have everything set at the 0.05 level. Hang on. Okay, so we have the alpha at the 0.05 level, right? So we know because we're looking for information in both ends of the region on both sides. We know that the z-score is going to be plus or minus 1.96. Again, that's that critical region. All right, so we know that the alpha is 0.05. That lets us know that our critical region is going to begin at plus or minus 1.96, because remember, we're looking at both sides for this. All right, so basically this is basically where the researcher is predicting that the education majors GPAs are higher, and that this particular sample, this particular sample is coming from a population whose mean is greater than the 2.7, okay? Basically, that alpha, this is the second sub-bullet under sampling distribution. Basically, that alpha, so right here, this is where I'm at. That's not quite what I wanted. All right, so this alpha is an indicator of rare events. So it's rare, we can basically say it's going to be rare that these differences are due to chance. All right, that's essentially what's being said. Any difference with the probability less than 0.05, that's our alpha level, is rare, and will cause us to reject the null hypothesis. Okay, so by saying that if our problem or our Z obtained falls beyond that Z critical, that's a rare thing, and we can reject the notion or the null hypothesis, which says there are no differences. Okay. All right. So step 3, basically, you are establishing that critical region. You know that your alpha is 0.015. And so that's essentially what part of what you would write down. You write down the alpha and then the Z critical. I think there's a couple of other little things Oh, you write the information about the sampling distribution. You write alpha, what the alpha is, and then you write what the Z critical is. And you can see examples of this as they work on the problems in the book. And again, I will demonstrate this as well when I do one of the problems. All right, so for 4, I'm actually going to compute this one out. I want you to see where it says compute the test statistic. Excuse me. Again, this is that Z obtained. Remember. So I'm going to go ahead and compute that. I'm going to go ahead and walk through the steps. So at this point, I will go to my OneNote. And just for reference, I put the information that we needed back up here. Remember, the population mean is 2.70. The sample mean, that's what this is. The sample mean is 3.0. The sample standard deviation is 0.70. And the number of people in our sample is 117. And we have an alpha of 0.05. So I could go ahead and say that my Z is going to be equal to plus or minus 1.96. Because remember, alpha, this is what we call a two-tailed test, which I'll talk more about later on in the lecture. But because we're splitting that alpha up between the two regions, we know that the Z is Z plus or minus 1.96. Okay. All right. So I have some information up here. One of the things that I'm going to do is I will round my calculations. Keyword on calculations. I'm rounding my calculations to the 3rd decimal place. But my final answer is going to be to the 2nd decimal place. Then once everything is said and done, I will draw out the curve so that you can see where the Z obtained is in relation to the Z critical. All right, so let's go ahead and get to it. Now, remember earlier, I think it was part of lecture 2, part 2 of the lecture. I talked about how I like to rewrite the formula sometimes. And because when I was working through a problem, I messed up and I multiplied something. This is that problem. I don't know about you, but there's a division symbol here that I didn't see it when I was working on the problem. And I've worked these problems many a times. And that's what made me remember, oh, this isn't right. And I realized you missed a critical step. So this is why I go ahead and I rewrite the formula sometimes. All right, so let me go ahead and I'm actually gonna rewrite the formula up here so that I don't lose space. So Z is equal to sample mean minus the population mean divided by the sample standard deviation, which is, you could do it like this, but either way, something that demonstrates there's division going on there. N minus 1, okay? All right, so now let's go ahead and plug in my numbers. So we've got Z is equal to 3.00 minus 2.7, because remember, these are all our numbers over here. I don't have the symbols, but at this point, you should, hopefully you know the symbols. If you don't, keep working at it. Just keep doing what you can to try and get those symbols drilled into your brain. All right, so the sample mean, which is 3, subtract the population mean. And we divide all of that by the sample standard deviation, the sample standard deviation, which in this case is 0.70, which is then divided by the square root of, and because we have a sample standard deviation, this formula, this calculation differs. Whenever we have a sample standard deviation, we divide by, we divide that sample standard deviation by the square root of the number minus 1. So that's why in this particular equation, the z obtained that I'm getting, you don't see n. It's because we don't have the population standard deviation. We have the sample standard deviation. So I have to divide that sample standard deviation by the square root of n minus 1, okay? All right, so n minus 1 is going to be 117 minus 1. All right, so what I'm going to do in order to save a little bit of space, I'm actually going to go this way with my, no, I'm not. I'll just work all the way down. I'll keep it vertical. Keep doing what I've been doing. All right, so now we have z is equal to 3 minus 2.7 divided by 0.70, which is then divided by the square root of 116, okay? Okay, so I told the tale. I'm actually going to go ahead and come over this way and do my calculations horizontally. So I'm going to start here, do a calculation, go horizontal, then come back and do the same thing. All right, so z is then equal to 3.00 minus 2.70. Do that. Be consistent. And then you take that and divide that by 0.70, which is then divided by the outcome of this number. So let's go ahead and get that. All right, so we know that 117 minus 1 is going to be 116. Square root of 116 in this case is 10.770. So we are going to divide 770. So we divide 0.70, divide that by 10.770. Now let's go ahead and come on over here and do the next set of calculations. So z is equal to 3.00 minus 2.70. And if you wanted, you could actually go ahead and do that calculation. I just like to do things in the order of operations. And in this instance, I need to get the denominator down to a single number before I do this. That's just the way I work and the way I do it. All right, so this right here is going to be, so this 3 minus 2.70 is going to be divided by the outcome of this calculation. So let's go do that calculation. All right, let's clear everything out. So I have 0.70 divided by 10.770. That is going to give us 0.064. All right, well, that 4 is actually, I'm just going to write down the 4. I'm going to write everything down to the 4th decimal, and then I'll show you why I put the number that I put here. All right, so that number is 0.0649. Okay. All right, so 0.0649. All right, so remember how I said we're going to the 3rd decimal place, which is right here. Well, the number to the right of this 3rd decimal place is 5. If it's 5 or above, we round up. If it was a 4, we'd leave it at 0.064. But because this is a 9, we're going to round this 4 up to a 5. So this number here is going to be 0.065. That is going to become, so that 3 minus 2.70 is going to be 0.30 divided by 0.065. All right, let me go ahead and do those calculations so you can see what I did, how I got 0.30. All right, so 3.00 minus 2.70, that's what gives us the 0.30. Then you divide that number by 0.065. And guess what? I got 4.615. So let me go ahead and do that. 4.615 equals to 4.615. Well, remember I said we're rounding to the second decimal place here. That gives us 4.62. All right, so now what I want to show you, remember I said that our alpha is 0.05. So just based on all the times we've gotten that number, we know that our Z critical, actually, let me do this. And this, because this is how you would write this out. We know that our Z critical is equal to 1.96. We know that our Z obtained is equal to 4.62. So when I go and I draw this out, all right, draw it out. Ooh, that's a little rough looking, but you guys get the point. So when I draw it out, remember, if I am doing, okay, so there we go. So this is my negative 1.96. This is my positive 1.96. All right, so at no point do we have a negative in this number. So we know that our Z obtained, our 4.62, is going to fall on this side, okay? Because remember, these are Z scores. So it falls over on this side. And what we want everything. We want our number in order for our hypothesis to be, for our test to say, yeah, there's a difference. We want that number to fall here. All right, so let me do this in red. All right, so this number, my Z obtained, is here, is 4.62. Well, it falls into our critical region. So what that tells us is there is a difference. We reject, because this 4.62 falls in the, so Z equal, 4.62 falls in the critical region. We can reject, writing too fast, you guys. We can reject the null hypothesis. Okay, that's what we want. However, if our Z obtained had fallen anywhere in here, anywhere in this area that I'm scrabbling in, if it had fallen in there, then we would say we failed to reject, okay? All right, so let's go ahead and go back to the, PowerPoint or to the lecture. All right, so that was step 4. All of what you saw me do, those were the calculations. That was what we do for step 4. I just wanted to make sure you got to see that and see how we got this number right here, how we got the Z obtained. This is stuff that you've already been doing, okay? But now you are putting all of these steps together. All right, so step 5. So basically what I just did with that normal curve, that's essentially what happened here. Now, because we are looking at 2 different regions, because we are just looking at, is there a difference? We're not asking about a direction for that difference. We're just looking at a difference. You know, that's why we have the plus or minus. So it's just, there's a difference. So Z critical is plus or minus 1.96. Z obtained is 4.62. And so, like I said, everything that I just showed you with the normal curve, the fact that that Z obtained, this score right here, the fact that that fell in the critical region, we know that we can reject the null hypothesis. So basically what's basically saying, if we were to state this in normal speak, we are basically saying that there are differences between education majors and everyone else. So like the very last bullet says, education majors have a GPA that is significantly different from the general student body, or you would say education majors have a GPA that is statistically significantly different from the general body. I know that's a mouthful, but basically, yeah, GPA majors are different, and those differences are real. It's not due to random chance. Okay. So that's essentially what's going on there. And that's step number 5. Now there's a certain way that you need to write it for the steps. And then the very last thing that you do what I'll have you guys doing and some of the problems for the assignments is you'll have to write up a statement, or I may say, make a recommendation to somebody based on the results of your hypothesis test. And you write those statements that I have you guys write. All right, so this is just kind of a summary. Basically what we're trying to do is identify statistically significant differences that are not due to chance, that there's something really going on with the sample, that whatever we said was the hypothesis, it actually, the test demonstrates that our hypothesis was correct, okay? So again, in this example that I just did, the difference between the parameter, the population mean, 2.70, and the sample mean, which is the statistic, 3.0, was large and unlikely to have occurred by random chance, because it fell so far out and it fell within that critical region that basically lets us know, yeah, this isn't random chance. Now, for some of you, you may look at this and you say, I'm not going to remember which thing I need to say, or I'm not going to remember what decision needs to be made. Well, this is what the table is for, this table right here. I don't remember what page it is in your book, but like I say with everything, if you need to write it down and put it in your notes, write it down and put it in your notes. Print this slide. Whatever it is that you need to do that's going to help you, do it, okay? And use this table to help you make those decisions. Draw out that normal curve. Yes, it is tedious. Yes, it takes longer, but guess what? You'll start to get the hang of it. And after a while, you might get to a point where you don't need to do it, but you do it anyway, just to double check what you're finding, okay? But draw it out. And if you see that test statistic falls in the critical region, you know that you reject the null. And that basically those differences that are being stated in that hypothesis test, those differences are real, okay? But if it doesn't fall in the critical region, this is where, okay, no, we failed to reject the null, so on and so forth, okay? What you don't want, what we've been working on in the past is, well, does the number we have fall within like the mean and the z-score? Does it fall in between those two? That's not necessarily what you want. You want to know, does it fall either beyond or below, okay? Does it fall on either side of the critical region? And again, this is where a lot of the stuff that you've already been working on is going to come into play. If you remember the stuff related to beyond the mean, where you had to find out, does something fall beyond the mean? Not beyond the mean, but beyond the z-score. That's essentially kind of what you're looking at here. If you need to go back and kind of refresh your memory on that, go for it. Or, I always say practice makes perfect. Practice a few problems, draw the stuff out, and see if you're getting the information correct. All right, so that actually is going to conclude part 3 of this lecture. And so I'll be moving on to part 4. This is where we deal with choosing a one-tailed or two-tailed test. So a one-tailed or a two-tailed test. If you notice, I keep saying we're on both sides of the region, and we're using the plus or minus. Well, in a one or two-tailed test, things differ. We start to deal with the direction of the hypothesis test, okay? All right, so take your break, come back, and we'll get back to it when you come back and when I come back.